we shape our own research directions, the way we choose them, is a mix of, it's like reinforcement learning. It's a mix of individual inspiration, inner intuition, but also very much the influence of the discussions with colleagues. And for me, visiting your center, discussing with you and your group has been extremely important in order to shape our project and research direction during the last few years. I had the opportunity to be funded by the Air Force lab, the Air Force programs that Fariba Faroo runs. I'm very indebted for this. This helped us also to keep the link with the US science community, the Humboldt Foundation that you mentioned, also the ERC, and well, of course, my home institution here in Erlangen FAU and the two universities in Autonoma and in Deusto, where yeah, I have fantastic colleagues that have helped me to develop this activity. So the context, we all know what the context is. I don't need to convince you. We know what ChatGPT can do for us. Somehow it's changing our lives the same way that Google changed our lives 20 years ago or 35 years ago. The emergence of personal computers over our desk changed also the way we could work. Nowadays, ChatGPT offers us the possibility of doing many things that you all know that were simply unbelievable 2 years ago. But on the other hand, artificial intelligence and machine learning is also affecting the way we develop the big science in a fundamental manner. So we see news in the newspapers very regularly. For instance, this one on the top left about the combination of is digital twins, right? Digital twin technology developed for plasma fusion. So plasma fusion is a very complex process. Of course, there is plenty we can do using the equations of mechanics and our understanding of dynamics and PDEs and numerics, but there is a point in which we really need to ask the computer to come to help us in order to handle data and understand complex phenomena for which we probably don't have a simple constitutive equation to be sufficiently accurate. And then, so here, down here, I bring you another breakthrough that I particularly like, in which you see how this interaction of mathematics, machine learning is occurring in an somehow alternating and mutually enriching manner. For instance, one of the last breakthroughs of alpha tensor using artificial intelligence was to develop new codes for multiplying, new methodologies for multiplying big matrices. So you see here today, we are giving a talk in applied mathematics in order to try to explain how artificial intelligence works, but actually one of the fundamental problems that applied mathematics has to eventually solve is also always multiplying matrices. Even if we start with 3D Navier-Stokes that nobody knows how to solve, and we build a very complex nonlinear solver, this nonlinear solver will be decomposed into pieces, and finally the key problem will be AX equal B or A times B, multiplying matrices. Well, artificial intelligence now is helping us also to multiply the matrices, very much inspired on the strategies that are employed, for instance, for solving complex Rubik cubes, or for defeating humans on games like chess or Go. So we see that mathematics can help to explain how artificial intelligence works, but artificial intelligence is also helping mathematics to move faster and getting into problems of dimensions that until now were simply impossible. And how this is done, as you know, for us that we are trained as mathematical analysts, in which, well, we have to first learn a lot of functional analysis, to later take courses or before or in parallel courses in continuum mechanics, so to be able to choose the right equations for elasticity or fluids or heat diffusion. and then combine our know-how on PDEs and analysis to gain a good understanding of what the solutions are doing, how regular they are. Then we take courses in numerical analysis, etc., to solve them computationally. But all our know-how emanates from our understanding of mechanics and the fact that these equations in mechanics are describing nature to an extent that is sufficiently accurate. In machine learning, we do the opposite. We say, okay, we don't take any of these courses. We have data. This data will be put together into a graph, into a network, a neural network, actually, in which each node of this graph will be representing a neuron. We will make this graph to be nonlinear. That's fundamental. There is a nonlinear activation function that is able to, in particular, discriminate negative and positive and split the Euclidean space into different parts. And in this way, out of data, we will be able to learn, to train, to compute the optimal parameters of this network. If this were a linear graph, we will say that these are simply A, W, and B are essentially the weights indicating how intense the link of one neuron with each other, the connectivity matrix of this graph is. But I insist, here is a nonlinear matrix, a nonlinear network. But after all, the problem is reduced to optimizing the parameters so that the discrete model we have adopted a priori, which might be simpler or more complex, deeper, wider, different architectures, different connectivity structures, depending on the model, we have a different number of parameters. But once the model is chosen, the architecture is fixed. It is just about identifying the optimal parameters so that the empirical risk is minimized, meaning that the data set we have is well represented, meaning that for every feature, the neural network is able to reproduce the correct label. So this becomes somehow a discrete dynamical system that is evolving horizontally, and we expect this nonlinear discrete dynamical system, very much like a Markov chain, to be able to bring every initial datum, which is represented by xi, so that at the initial layer, after evolution, when we get to the final layer indicated by the index capital K here, we match the label. That's the idea. Okay, so the problem becomes optimize this discrete model, identify the coefficients, and try to see whether the architecture you have chosen is sufficiently good to represent the data you have. If the architecture is not able to do it, probably you need to enrich it. You need to add more neurons. Maybe you need to add also connections or make it more complex. And at the moment where you really feel comfortable that your data have been well represented, then you are basically done. You can start checking the next step is whether, this neural network is able to generalize well. Now, the point, so this image is taken from this dissemination page, 3 blue, 1 brown, where there are very interesting videos describing in particular the functioning of neural networks and artificial intelligence. The point is that, for instance, in ChatGPT 3, in the free version, free version, the number of parameters is 175 billion. Okay, so the graph I was plotting before was really a baby model compared to the monster we have actually to deal with and to train. So you are immediately facing the course of dimensionality. And not only this, also the devil of non-convexity, because although here everything looks quadratic, nice and convex, as I said, there is an activation function, non-linear function entering in each of these neurons. And I recall you that the composition of two convex functions is not convex. So as soon as you make the model nonlinear, even though here this looks quadratic, the overall functional you are willing to minimize is not convex. So you have somehow two devils to defeat. One is the course of dimensionality, and the other one is the lack of convexity. Okay, so This is a very rough presentation of how things were developed by, the computer science community. Of course, there are decades of work, very intelligent people working here, and they have, bring us to the point where we can use, speech assistants like Siri, or we can use ChatGPT and many other fantastic devices. So we have to really recognize that, the work that this community has done is really amazing. And this is why probably this year, for instance, the Nobel Prize of Physics was delivered to people who contributed to this area of artificial intelligence. Okay? So from a math perspective, what can we do? We can do many things. So there are many people that nowadays are from the applied math community interested in machine learning-like topics. But in fact, when you listen to the different talks, you realize that, there are very, very different questions that they need to be somehow well classified to better orient our efforts. I will try to very briefly here talk about three questions. One is, and this is something on which all efforts from the math community are very welcome, and this will not only be done using tools of, sorry, this will not be done only using tools from, this will not only be done using tools. Can you hear me now?
Yeah, perfect.
Okay, not only be done using tools of PDEs or ordinary differential equations or control theory. This really requires the involvement of all communities, probability, statistics, approximation theory, Fourier analysis. So the main first challenge is try to develop a mathematical theory explaining why and how this works so efficiently, because it does. The second could be we are applied analysts. We are used to, after all, work with models arising in mechanics. We need efficient tools to solve these equations. So how can machine learning technology help us develop new computational tools? And maybe the third one is a topic to which I was introduced by Harbir. Actually, last year there was a fantastic workshop on digital twins he organized in GMU. I had the opportunity to attend. And well, digital twins as the side, the scientific area in which data, mathematics, models, and decisions collide. I think this definition is taken from the report of the American Academy of Sciences. So digital twins is an emerging area in which all these efforts can be and have to be combined. And I will say that probably from a purely math perspective, there is a new area emerging that I like to call PDE plus D, right? PDE for partial differential equations plus D for data. So this will be the PDE version of what a digital twin is. Okay, so let me first go to the first question. Why does it work? Actually, why it works, the first results in this direction were already published by Norbert Wiener, who, by the way, was the one who in 1948 wrote later the book on cybernetics, the foundations of control sciences. So Norbert Wiener in 32 wrote this 100 pages paper in Annals of Mathematics, maybe his PhD, on Tauberian theorems. So in that case, he was thinking on approximating functions just using Gaussians and translations of Gaussians. It took 57 years from the paper of Wiener to the paper by Sivenko, in which he did basically the same, but replacing the Gaussian function by the sigmoid function, which is this smooth front, moving from 0 to 1, from 0 asymptote minus infinity to 1 asymptote. What was the step here? Well, actually, when Wiener proved his Tauberian theorem, he used fundamentally the Fourier transform, and he needed an activation function whose Fourier transform were non-zero everywhere. This is why the Gaussian is a very prototypical example, because as you know, when you take the Fourier transform of the Gaussian, you get the Gaussian again, and it's non-zero everywhere. While by the contrary, when you take the sigmoid function of Cybenko, the Fourier transform of this function will certainly have an oscillatory nature. You cannot apply the result by Wiener. But what Wiener didn't think at that time was that this scaling term, or at least he didn't use it, is that this scaling term, y here, which is multiplying the variable x, and therefore is scaling, is stretching or dilating the activation function sigma, making this transition either sharper or milder, he didn't think on the use of this y. The theorem by Wiener was only based on the use of the parameter alpha for amplitude and theta for translation. Then what Cybenko observed is that if you use this parameter y2, then you have this density property that already Wiener proved, and that was renamed as the theorem of universal approximation, which is one more theorem of density. We know many, Stone-Weierstrass, Fourier series, eigenfunctions of the Laplacian, and many other. Well, this is another one. Not, however, that in this ansatz, we know also the density, for instance, of finite element functions, P1 functions. So this ansatz, however, is different because there are, of course, there is n. The number of terms you need in the series has to grow in order to approximate general functions. There are, of course, the weights alpha that have to regulate amplitude. That's natural. But there is something that is new with respect to classical approximation theory here, is the fact that these two parameters, theta and y, enter on the activation function, this basis function sigma, in a nonlinear manner. And it's the fact that these parameters enter in a nonlinear manner that makes these ansatz to belong to the category of nonlinear approximation methods. Note that the paper by Cybenko was published in the first year, 89, of this journal, Math, Control, Signals and Systems, that I think at that time was launched by Willems and Sontag, two celebrated control theories. You see that there was already from the very beginning a very close link between the two fields, right? So on one hand, Norbert Wiener doing the first results on the universal approximation theory and being the one that established the foundations of the field of cybernetics, and on the other hand, Cybenko publishing his paper on a control journal. And in fact, there is a very clear link. You see, for instance, here, a classical control application in which 4 dogs in blue are herding a flock of sheep. So this is not easy. I mean, this, you need to build a good model for this asymmetric predator-prey or driver-follower interaction. But the tools of optimal control, when properly applied, using optimality system, gradient descent, good numerical solvers for ordinary differential equations, lead to this optimal kind of a strategy in which is not so intuitive. You see that 4 dogs dancing, moving diagonally from southwest to northeast, are building a corridor along which the sheep are moving. They don't know what they are doing. They are simply avoiding the proximity of the dogs they are afraid of, and by doing this, they are getting to the gate that is located on the destination. On the right-hand side, you see a video from deep learning in which you are simply observing how a deep neural network evolved, a deep neural network that has been trained in order to classify, for instance, tennis balls of different colors, the yellow, the purple, or the green, the same way you classify students on campus depending on the faculty to which they belong. So normally on the right-hand side, we say, oh, the video on the right-hand side is machine learning. The one on the left is control theory, and there is no link. But in fact, there is a very close link. The only difference between these two is that here in machine learning, normally we pre-compute the parameters that are guaranteeing the success of the deep neural network on this classification task, but normally we don't consider these parameters as control. The day you realize that they are controls, then you are on the boat. The link between these two fields is extremely clear, and you can employ tools from one into the other and vice versa. In fact, this is not new. I mean, nature. So you see, nature knows this. Here you see two dogs, border collies that are able to segregate ducks according to their colors. And now, if I ask you, can you please tell me whether the video of the border collies belongs to the category of control theory or machine learning? I will tell you, well, definitely belongs to control theory. Here we have 4 dogs and 100 sheep. Now we have 2 dogs and 20 ducks or 30 ducks. Here the goal was to bring all sheep to destination together in a single crowd, in a single flock, while in the dog duck game, the dogs have as target to split the crowd of duck according to their labels. And then this makes the video of the dogs and ducks closer to the one in supervised learning or machine learning, because the task there was rather build a deep neural network that is able to classify. So we see that all these things are built up in nature. We know and we do them in our daily life without even thinking how we are doing it. And control theory, both control theory and machine learning, twin topics, they come, to somehow help to understand how this has to be done in a systematic manner. Now, when you want to analyze this from a math perspective, it's good to have a model. After all, we follow Newton, ODEs, dynamical systems, and control theory tradition. This is the model of Sibenko, a static model in which a very tall static neural network has to assure density. What people realize is that instead of doing this in one shot, piling up many, many neurons, it will be better maybe to do it gradually through this time discrete system. And once you describe this time discrete system that way, you realize that this is the time discretization of this ODE that we will call neural ODE. Now, this ODE, contrarily to the classical ODEs coming from mechanics, is purely synthetic. It's purely artificial. I have built this ODE simply because I like it, with a nonlinearity sigma, which is typically nowadays the ReLU, very simple Lipschitz function taking 0 values to the left and linear to the right. It could not be simpler. The nonlinearity being Lipschitz, this ODE is well posed. And here I see the parameters W, A, and B in the static ansatz of approximation theory of Wiener or Sibenko now become time-dependent controls. Now, let me explain you why this works. So this is a different application. Here, the goal is, for instance, to classify trash. Can I classify trash using neural differential equation? And the answer is yes. Let me explain you why you can formulate this problem in which you want to build a robot able to classify trash, how this robot can learn through the lens of this neural differential equation. How you can do it? You take any of these items that for us as humans is very easy to recognize. Of course, we can do that. We don't need a robot to do that, but we don't want to do that. We don't want to spend our lives classifying trash. So we prefer to build a robot, teach to a robot to do it so that we can be free to do math. So plastic is yellow. Glass has to go to the green, paper to the blue, organic to the gray. So we take a picture of every item. Every picture, low resolution or high resolution, is a number of pixels. This goes into a Euclidean space of dimension d, and then we can, for instance, in dimension 2, allocate to every basket one of the polar coordinates, polar extremes, right, on the coordinate axis. And we formulate a problem in which we need to build an evolution so that every item gets to the corresponding basket, but respectful to the corresponding labels. And this is what I have shown you before. You can do that in this application with 3 colors. You consider this model. You train using control techniques. You train or you identify, you build the controls W, A, and B optimally so to fulfill the task. And when you run the dynamics, you get it. You see that contrary to the very classical problems in control theory, in which you are trying to send a rocket from Earth to Moon, and then whenever you change the trajectory, you have to change also the control. Here we are aiming to solve this giant simultaneous or ensemble control problem, according to the terminologies that were developed by Lyons and Brocket, simultaneous or ensemble control problems in which all trajectories have to be controlled simultaneously. So the fact that this can be done was published in our paper in Science Review last year, Domenech Ruiz-Vallet, in which, you know, the statement can be very long, but basically we say, once you think that way, if you are in dimension 2 or higher, not in dimension 1, because in dimension 1, if you try to classify items, they will collide. You need to be in dimension 2 or higher. If you are in dimension 2 or higher, you give me any number of items n, you give me any number of categories, labels m, I will always be able to find controls which are piecewise constant, are of bang time, with a finite number of switches, and that are able to bring all the initial data simultaneously in an ensemble manner to the corresponding classes. So the theorem says, yes, we can using this model of neural differential equations. Of course, this is very much related also to the theory of optimal transport, except that here we will say this is a neural transport in the sense that, of course, ODEs are characteristics of transport equations. So if we were able to build ODEs using these smart neural differential equations that were able to bring initial data to the corresponding destinations in an ensemble manner, we are building also transport equations that are able to drive multi-atomic Dirac measures, atomic measures, into the corresponding destinations. So there is also a clear link with the theory of optimal transport. But to better explain why this works, let me tell you a bit more. The way this works is really very much inspired on the Rubik cube resolution, in which we do iteratively a finite number of motions in which half of the cube remains frozen while the other one rotates in a strategic manner. And you see that this neural ODE is precisely what it does. Think on, for instance, one of these plastic bottles that is evolving in the d-dimensional space to try to get to the yellow basket. You freeze time, and then you watch what this bottle is doing, xt. Now, you look to the derivative, x prime, x dot, time derivative of the particle at that time, and to see in which direction this particle is evolving, you look to the right-hand side. And on the right-hand side, you see sigma. Sigma has 2 options, either 0 when a dot x is plus b is negative, or sigma then linear identity a dot x plus b in case the quantity here inside is positive. But what is the separatrix here? The separatrix is a dot x plus b equals 0, and this is just the hyperplane perpendicular to a and shifted according to the scalar value b. So you see that with one hand, at any time, you are choosing a and b, and these a and b are simply splitting the space in which data are evolving in two halves, and then the activation function sigma is the one that is responsible to say, once a space is split into two halves, one is frozen while the other one is evolving. And in which direction the other one evolves? Well, you have the left hand free still, in which you can choose the direction of the wind given by W. So you see that basically you have two controls. AB on one hand is just cutting a space into two, and the W is the one that allows you to choose the direction of the wind, but also on the half active part of the Euclidean space. And in this way, you can prove by induction that one by one, you can, as I said, classify arbitrary finite sets using controls with a finite number of jumps. And here I show you how you can do it in a very simple example in which you have 9 points. 8 of them are in the corresponding basket, but you see one that is badly collocated. The exercise is, can I choose piecewise constant control so that the blue will go to the blue basket? Of course, keeping the others in the corresponding baskets. And the answer is yes. In this case, this very simple motion is not optimal. It uses 4 piecewise constant controls in which you cut a space horizontally and vertically, and then you move it, choosing the active part strategically, and you see how little by little the blue gets to the blue, the others remaining in the corresponding classes. So this is just the starting point of the induction argument that explains why control theoretical ideas allow to guarantee the simultaneous control of this neural ODE, which is the response to the problem of representation of a data set, of classification of data, as our two kind dogs were doing with the ducks. Now, the second topic is how can I use neural networks for solving PDEs? There is a lot of activity on this. There is, for instance, PINS methodology that has been very successful in this area. Let me just take a very simplistic PDE perspective. Let us think on the Laplacian, for instance. Well, the Laplacian, the Dirichlet Laplacian, we all know. The solution can be found using the variational representation in the space H10. We know the solution, the weak solution of the Laplacian is just minimizing the energy. And we also have the finite element theory that says if you replace here in this minimization principle the full H10 space by P1 finite element spaces, of course, you don't get the full minimizer, you just get an approximation, but this approximation is H close to the minimizer. This is just a very brief introduction to finite element theory, okay? And this works. Now, if you we learn and we were curious about what this kind of Sebenko neural network ansatz can bring, we can say, well, why I don't do the same, but instead of using the finite element ansatz, using the Sebenko ansatz. After all, when I compute here, if I take k neurons and I check, so A is a vector, D components, one here, one there. So this is a manifold of dimension k times D plus 2. So I can also minimize this energy over this manifold. The minimizer will exist. And then if I work a little bit, right, using the classical ideas of gamma convergence in the calculus of variation, and I use the fact that this manifold guarantees the universal approximation theorem density, I will be able to show that the minimizer of this problem converges to the minimizer of the energy in the full space, which is the solution of the Laplacian. And then I say, oh, you see, now I have built a neural network model or method in order to solve PDEs, the simplest PDEs at least. But you see, there is a catch here. So here, when we were doing linear approximation theory, this problem was convex. And therefore, the minimizer exists because I apply the direct method of the calculus of variation, and I can apply gradient descent to guarantee the convergence or some conjugate gradient method in order to converge efficiently to the minimizer. The same can be done in the finite element setting because I am adopting a linear approximation paradigm and such. While here, as I have explained in the beginning, even if this functional looks nicely convex, because this manifold here is extremely nonlinear, this problem here is non-convex anymore, and therefore you will be obliged to use a stochastic gradient descent method, which, as you know, converge in expectation, but doesn't give you the same level of certainty on your approximation procedure as classical numerical analysis did. You might be satisfied by this, the convergence that, in expectation that the stochastic gradient method, leads to, but you have to know that you are not getting exactly the same thing when you replace the classical finite element ansatz by the neural network one. There is a remedy for this, and this has been well known by now in the community of machine learning. This is a classical relaxation procedure, very much like Young measures that were used in the calculus of variation later by, Tartar, Di Perna, and so on for solving conservation laws. This is a very classical relaxation procedure. You can observe the following. Well, in the ansatz of Sivenko, well, now K became P. Okay, it's just a detail. This is the ansatz of Sivenko. This is nonlinear on the parameters A and B, is linear on the parameter omega. But you can immediately make this sum to be linear, provided you extend it into an integral. So if you, out of the activation function sigma, that was just a function depending on a scalar function, on a scalar parameter on the real line. Now you build a function sigma, which depends on the d parameters A, the d parameters B, and the parameter B. And now, in case this function now, which is a new function depending on these three parameters, A, X, and B, you will integrate this function continuously with respect to the parameters A and B against a given measure mu. What do you get? Well, of course, you get a function of X. You have a function depending on A, X, and B. You integrate with respect to A and B, then you get a function of X. Now, what happens when this function of X what happens when this function, this measure mu, is atomic? This is just a number of Dirac deltas located on some specific values of A and some specific values of B. Then you see that whenever the measure mu here is atomic, you get precisely to the ansatz on Sivenko. So this is just a relaxation procedure. Whenever you are living in the space of Dirac deltas, the approximation methodology is going to be nonlinear because the dependency of the Dirac delta on the support, right? Not the amplitude is fine, is linear, but the support of the Dirac delta, the dependency is very nonlinear. While when you move to this setting of relaxed measures, the problem now becomes linear in mu. So you see that we can, out of this problem, that because we were using neural network, we made it nonlinear, we can make it again linear and convex and nice. But what is the price to pay? The price to pay is that we are back to infinite dimensions, because now we will have to minimize the Dirichlet energy based on this generalized or relaxed neural network ansatz involving measures. This is why I have put here the elevators, because we took one elevator down in order to go from the infinite dimensional setting of the Laplacian, right? It's functional analysis, infinite dimensional functional analysis. We were very happy to go down using neural networks to the finite neural network ansatz. But in order to understand it well, because of this devil of convexity, of the lack of convexity, we have taken another elevator, which is the one of relaxation, that brings us back to the infinite dimensional setting. Somehow, there is some justice here. Problems are deep. And there is plenty to be understood from an applied mathematical perspective to say for each problem which is the best strategy. In particular, should we simply do like this and apply blind stochastic gradient descent? Or should we rather think on the possibility of using relaxation? And in case we do that, given that we are going back to the infinite dimensional setting, did we gain something with respect to the original problem of the variational formulation of the Laplacian that was from the very start infinite dimensional as well? These are very interesting questions from an analysis and a math perspective, an applied math perspective. So you see, until now, I have mentioned two different classes of problems in which we as mathematicians, when facing artificial intelligence and machine learning, we could position ourselves and consider. One of them, why does it work? Of course, there are many other directions of work. There is, approximation theory. There is geometry in high-dimensional Banach spaces. There is probability theory, statistics, dynamical systems, numerical analysis. There are Fourier analysis. There are so many different ways in which you can try to explain why these objects are working so well. So here I have just taken you our, say, modest perspective of explaining that, in fact, control theory also provides a positive answer. And this is natural because these two topics are linked from the very beginning, starting from the works of Wiener, right? Continuing with Sivenko, and as we have seen, actually embedded in nature, in which the animal behavior or the human behavior really obeys in a way that is somehow in between, control theory and machine learning, which is actually the spirit of reinforcement learning, right? That, as you know, is somehow a very smart and efficient way of solving two problems simultaneously, the one of identification of the model and the one of control. Of course, we as mathematicians, we teach to students different courses. One course is for inverse problems, and the other one is for controlling the model. So we say, first you have to do the inverse problem to know what the model is, and then you have to do control once you know the model is. And in practice in life, things are not that way. In practice in life, we control systems that we don't know well, and according to the behavior of this input-output box, black box, we learn better about the model. And because we learn better about the model, we control better. And each time we control, we learn better about the model. So it's kind of an alternating use, simultaneous alternating use of inversion and control. This is what reinforcement learning does. This is what these dogs are doing with the ducks, right? And this is what you see when you implement control theoretical ideas for machine learning. Now, going to the third topic about how to use these tools in combination with classical mechanics for modeling. Well, there is a very first remark that we indicate in this paper in collaboration with postdocs in our team, Siki and Lee, Can Liu and Lorenzo Liberani. Can Liu now got a position as associate professor in France, in Dijon. So the first starting point was the following. We said, listen, because we have shown that a neural differential equation can take a number of initial data and bring them to the corresponding location at the final time, we can iterate this procedure, and we can do it in a way that, for instance, if you tell me that there are 7 or 8 sensors, for instance, measuring wind in different locations in this region where I am, in Erlangen, and then they are doing it every 10 minutes, and you are getting these new records every 10 minutes. So the records at the initial time were the black positions, on the plane. These, thermostats or sensors are giving me 2 values. This is why I represent they are giving me direction of the wind and intensity of the wind, for instance, 2 values, or humidity or whatever. So I represent it on the complex on the plane. And I tell you, initially are the black dots, later are the blue, later the green, later the red, later the yellow, and so on. And I ask you, can you build an artificial neural network-based model that is able to track all this data? And the answer is, of course I can. Why? Because I know how to match t equals 0 to t equal capital T. I can repeat that again and again and again, and then the model will do exactly what I need. I don't think the video is working here.
It was working for a second.
I see. It was, yeah, I'm sorry, because I'm watching the wrong screen. Yeah, it's moving. Okay, so no surprise. I mean, you can build a neural synthetic differential equation exactly with the same answers as I have shown you before. And this neural synthetic differential equation will really interpolate the data at the correct time instances. And you could say, well, I have built a synthetic model that is able to record all this data. Of course, the question then is, well, yes, you can do that, but how reliable will be this model when you try to use this model, for instance, in order to anticipate future weather evolution? Or whether you can use this model in order to guess what wind evolution will be on a different location that is not really the one represented by any of these sensors. So this is unlikely to happen, right? Because I have overfitted that much. I have so much pay attention to make that this synthetic model passes through exactly these points, that is very unlikely that when I try to extrapolate and generalize, this will give me very relevant information. Let's move further. So what we observed in that concerning in particular whether I can use these ideas in order to move into the future, we made the following observation. This is something that is obvious, but it's good to state and realize that way. So think, for instance, that we are dealing with a complex non-autonomous dynamical system given by this nonlinearity fx, t. Of course, when the dynamical system is non-autonomous, is time evolving, you agree with me, having information about what happens in the past, 0 capital T, doesn't tell me much about what's going to happen in the future because I don't know. I mean, the nonlinearity f could switch completely and behave differently after capital T. Now, the ansatz of neural networks has some advantages. Why? Because if you apply, for instance, the typical ansatz of Sibenko to this function f, where now, of course, the function f depends both on x and t, and therefore x and t are now a new variable, x living in the space rd plus 1, right? So we merge the space-time into a single multi-valued Euclidean variable. When you write down this ansatz a la Sibenko, what you see is that now the same way we have the scalar product of the corresponding coefficient a with x, you have the scalar product of a with t. So, of course, this model is going to be, again, non-autonomous, right? Because it depends on t. But you see, it's non-autonomous in a trivial manner, meaning, in particular, that if you were able, out of the data you have in the past, you could guess what the A is, you have an immediate guess about the behavior of this dynamical system towards the future. So one interesting working direction that we are trying to explore, of course, once you do this, you cannot expect that the proximity of the original dynamics and these semi-autonomous dynamics where A is frozen in the past and you stick and you keep this kind of neural network ansatz, you don't expect that they will stay close for very long. But you have a starting model to begin with, and then we can use the ideas of model predictive control, of iterating in order to push farther and farther towards the future. So this is one of the ideas that we are pursuing in this direction of combining modeling and neural networks. The other example I wanted to show you is, this is joint work also in collaboration with Weiwei Liu. She's a professor in the University of Atlanta. we were motivated by our joint interest in fluid mixing. And for fluid mixing, there is a fantastic example, a paper by Doswell, not well known in the applied math community. It was published in a journal in meteorology 40 years ago. And in this paper, he gives a fantastic explicit transport equation, is totally explicit, in which you build a rotatory, vector field G, right, that generates this kind of tornado dynamics in which out of this flat interface separating two fluids, the red and the blue, little by little you see this spiral emerging, this tornado emerging, right? And not only you can see that numerically, but actually in this case, you have a complete explicit solution that allows you really to track how the regularity and the twisting of this interface evolve. So here you see two different simulations. You can nearly not distinguish. Of course, there are some differences, especially by the end of the time, but this is the exact one, and this is the one we get using these ideas of neural network approximation. I give you here an example in which now what I have done is we have taken a number of sensors, quite many, of course, this is why our resolution here is good. We have taken a number of sensors. These sensors are tracking the evolution of this transport equation, so we are giving exact information or nearly exact information about how the characteristics starting from these points are evolving, right? And then using this neural network construction, as I have mentioned before, we can generate a model that is purely synthetic. So in this model, we don't know the true vector field V that generates the Doswell dynamics. We only know the partial information that these sensors provide. And despite of this, we are able to build a neural network vector field that is able to mimic, at least in a qualitative manner, the behavior of this Doswell frontogenesis or tornado. Of course, if you ask, well, but how precise this will be when you are looking closer to points which are not really represented by the sensors, of course, there is lots to do in this direction and there is no magic, right? So, I mean, with the given information you have, you cannot more representation accuracy that the one these data allow. After all, concepts such as Kolmogorov complexity should be here taken into account, not to expect that with n parameters you can do better than the intrinsic Kolmogorov complexity of the model allows. By definition, this complexity level is the best you can expect out of n parameters. But still, you see, here I'm mixing a little bit ideas. In order to conclude, I would like to make you a proposal. This is another direction in which we are working. And I think it can be extremely valuable, and it goes very much in the direction of digital twins. Actually, I think that I thought on this kind of methodology when I accepted the challenge by the invitation by Harbir to deliver a talk in his workshop is the following, and I will conclude with this. So we have mechanics. Out of mechanics, we have PDE models. So if you tell me that you are interested on, I don't know, the diffusion of a given population, insects in the fields, I will tell you, well, diffusion is certainly a diffusion model. But of course, even if you open the book in, math biology, you will see there are plenty of diffusion models. They will tell you, listen, you have to model the nonlinearity. You have to model the parameters on the model, the density, the velocity of propagation, the birth rate. There are plenty of parameters in such a model. So even if we use mechanics, we get to a class of models, but this class of models doesn't really tell us what model you really need. This is why we need inverse problem theory in order to match the parameters and the nonlinearity to the data you have. And the tradition of inverse problem theory has been, for instance, in the Calderon problem, has been to show if you know many, many, many solutions, right, you will be able to identify these coefficients, maybe even in an exact manner on a given class. We also know these inverse problems are typically ill-posed, and therefore, from theory to computational practice, there is a huge gap. Here, our perspective is a little bit different. So I'm not trying to solve inverse problems. So I don't assume that I have all the information I need about, for instance, the Dirichlet to Neumann map. I just have the data I have. But what I have learned now is that out of the data I have, I can build a purely artificial model, synthetic model, a residual neural network or a neural differential equation that is able to track this data exactly. Of course, when doing this, there is plenty of room, right? So there are many vector fields that fit, into this neural ODE, will be able to track this n finite number of data I am tracking. So there is plenty of room here, and there is plenty of room there. So the research direction we are trying to pursue is to show that if you adopt this dual perspective, then a collapse strategy that will be simply basically be minimize the residual. This will lead you to the best possible models. Why? Because when you push the PD solutions, the PD model, to copy, to mimic the dynamics that the transport equation emerging for data is realizing, somehow you are teaching the PDE is learning from the data. On the other hand, when you are pushing the transport equation purely emerging out of synthetic information to get closer to the family of parabolic PDE, you are indeed also enriching your purely synthetic model by these phenomena that mechanics tell us are essential, like, for instance, this onion ring propagation in diffusion processes that will certainly then distort the nature of your vector field. So this is the PD plus D approach, very much related to many others like PINS and many other alternative approaches for this merging of machine learning and traditional numerical analysis. And again, I insist there is, in my opinion, plenty to be done, and you are all welcome to join. I will be very happy to discuss the topic with you. There are a list of open problems that I bring here. I will just to mention two different categories. I think it's good to classify them. One will be the more fundamental questions of math for learning, and the others will be more practically oriented problems with the aim of developing efficient digital twin methodologies. Thank you for your attention and your invitation again.